So the plan for today is basically to continue talking about limits. Well, first to solve some the plan is to continue talking about limits, and first we'll solve some examples, just a little bit more complicated than we've seen last time, and then we'll talk about different kinds of limits. So I'll start with just a warm-up. Instead of two questions, similar questions. Okay, so the questions are the following. First one asks to find the limit as x tends to 3 of x squared minus 9 divided by x plus 3. The second one is about x, and that's, x squared minus 9 divided by x minus 3. Let's start here. So, how do we solve such a question?
You factor them out, so you become x plus 3
Okay, that's a good idea, but maybe not even the best. I mean, yes, it is. It will work. Let me explain why it's not. Well, let me explain what's a little bit better idea. So, before we start doing those great manipulations to expressions, even if it's kind of your first reaction when you see x squared minus 9 factoring x minus 3 times x plus 3, well, you don't have to in some cases. In this particular case, the first thing you should do is just check whether the most naive reasoning would work. When x is close to 3, you want to understand what is this expression close to. So what is the numerator close to? Well, 0. 3 squared minus 9 is 6. The denominator is close to 3 plus 3, which is 6. So we are basically, in this process, dividing a small number close to 0 by something which is close to 6. Of course, we are going to get still a very small number. So here, without doing anything, we just see that it is 0. A small number divided by 6 is still a small number. And maybe let me write in parallel a different example, but of the same kind. If you want to compute limit, say x to 8 minus 3 to the power 8 divided by x to the 7 plus 7 squared plus 7. So this example, even though it looks more complicated than this one, we have high powers here and complicated expressions, it's really not more complicated. And here you see that you really don't want to factor it, because it made it hard to factor it. On the other hand, you see that the numerator here, when x is close to 3, is close to 0. So numerator is a small number. The denominator, to think in the bottom, well, it is something. It is 3 to the 7, close to 3 to the 7th plus 7 times 3 squared plus 7. It is some positive number. Some particular positive number. I don't know what it is. I didn't compute it, but it is a positive number. And then I divide a small number by some definite positive number, non-zero number. Well, the result is still a small number. If you take a small number and divide it, say, 125, I don't know, maybe it is 125, maybe it's larger, maybe it's slightly smaller, but you still are going to get a small number. So this example shows that, well, sometimes you don't have to do any algebra, any complicated things, just, well, it's not exactly substituting, but almost. I mean, the argument is not that the value of this function at the point 3 is equal to 0, but rather, well, yes, the function at this point is 0, and also when the argument is close to 3, the value of the function is close to the value of 0. So that's the additional thing. For this example, let me move it a little bit higher. I would say that we in all examples, we would have to start with the same reason. We'll have to argue what is the numerator like, what is the denominator like. So when x is close to 3, the numerator is close to 0, and denominator is close to 0. So we are dividing a small number by another small number. And we do not know what is the quotient of two small numbers. I mean, really, if you have two small numbers, quotient of small numbers we really don't know what it is. You can take, say, one small number like this, 0.002, another one 0.001, and get a quotient of 2. But you can take other very small numbers and get drastically different results. For example, 0.02 divided by 0.1 will be, well, 0.02, so quite small number. Or if you take the opposite way, 0.1 divided by 0.001, you'll get 100. So you see that you can take small numbers, divide them by each other, and get drastically different results. So you can apply this kind of reasoning. On the other hand, well, as you suggested, we can factor the numerator. We can see why it actually tends to 0 when x tends to 3. And the reason is because it is a product of x minus 3 and something else. In this case, x plus 3. And now we are asking what is this quotient close to when x is close to 3? Well, we can cancel out this x minus 3. Because we are not asking what is the value at point 3. We are not talking about x equal to 3, just close to 3. So we can cancel it out and get that it's the same as limit as x tending to 3, x plus 3, which is 6. Right? So you see, the first step in solving questions is always try the most naive approach. Often it will not work just because, well, on an exam we won't give you the simplest questions. On the other hand, when it does, well, it's great. It just works. You don't have to do any algebra, any calculations. Okay, so let's maybe questions about these two examples. Okay, let's maybe discuss another one, somewhat similar example. Limit as x tends to 1 x squared minus 3x plus 2 divided by x squared minus 4x plus 3. Well, so what is the first step? Yes, try to see what happens to the numerator and denominator when x is close to 1. That's always the first step. close to 1, what is the numerator close to? It's close to 0. Maybe it was, if it were even more complicated, let's just write it down. X squared minus 3x plus 2 approaches, as x approaches 0, it approaches 1, it approaches 1 squared minus 3 plus 1 plus 2, which is 0. So, if you want to do some relatively complicated algebra in between, just make a small remark. As x tends to 1, this number tends to 0. It's just a different way to write a limit. And similarly about the denominator. When x tends to 1, the denominator tends to 1 squared minus 4 times 1 plus 3, which is 0. So we made some computation. It's for us just a remark. It's not actual answer, but we just see that, well, we can't do the most naive procedure. Okay, so this didn't work. What's the next step? Split. Yes, let's try to factor. Now, there are two ways to factor such expressions. One is kind of the most straightforward. You have a quadratic equation. You want to find its roots, solve the quadratic equation by the usual formula. I claim that it's actually not really necessary here. You can do it in a simpler way. The reason is because what are you trying to do? You want to write it as x minus something times x minus something else. So we want to find the roots where this polynomial is equal to 0. Well, we already found one. Which one? Yes, you said it right. Right. We already found that at the point 1, my polynomial is 0. So I don't have to guess the roots. I already found them. One of them is x minus 1. Well, the other one has to be something. So x minus, yes, 2. So for instance, you see that the product must be equal to plus 2. Similarly in denominator, I already know that it vanishes at x equal to 1. So I factor out the x minus 1, and then I'm left with x, well, minus 3, right? Once again, the product should be plus 3. And you see that, well, the expressions do match. So I did do the factoring correctly. So in a sense, I didn't even have to solve quadratic equation. It's even simpler than that. And now I can quite easily evaluate the limit. I can cancel out x minus 1. As we said, we are not interested at the point x equal to 1, just nearby. And the quotient is, well, the numerator is close to minus 1, denominator is close to minus 2, so the quotient is close to 1/2. So the answer is 1/2. Okay, any questions? Did you have a question? No? Yes.
No.
Okay, so any questions? Other questions? No. Any questions? So the point of this exercise is, well, one of the points is when you see complicated expressions and you can't evaluate the limit most naive way, try to factor. Second point, you don't have to factor completely. You just have to factor out the part which makes the expression tend to 0. In this case, x minus 1. Okay, let's move on. Let's solve such. such an example. Limit is y tends to 9, y minus 9 divided by square root of y minus 3. So like always, first step, let's check whether we can do it by bare hands, just actually dividing. So when y is close to 9, y minus 9 is a small number close to 0. Square root of y is close to square root of 9, which is 3. So square root of y minus 3 is once again a small number close to 0. We are dividing two small numbers, we don't know a priori what we are going to do. So we'll have to do well, something about it. Some algebraic manipulation. So what is it? I mean, somebody said something. Yes, let's see. Multiply and divide by conjugate. Yes, that's one of the solutions. So one idea is as follows. We have a funny formula. A squared minus b squared is a minus b times a plus b. So sometimes when we have square roots, something like this. Square root of a minus square root of b times square root of a plus square root of b. The product is a minus b. So sometimes we can simplify expression with square roots by using such a formula. And in this example, it works like this. We take the expression y minus 9 divided by square root of y minus 3. Well, I don't have exactly this situation, so I will create it. I will artificially introduce this conjugate term. I'll multiply the denominator by square root of y plus 3. Now, there is a problem with just doing this. The problem, well, I changed my expression. It used to be this one, now it's a different one. Now it's a different row. So to make up for this, I'll multiply by the same expression in the numerator as well. Now my expression is exactly the same. Well, I just multiplied both numerator and denominator by the same number. I didn't change the fraction. And it might seem that I actually made the expression more complicated. But there is a reason why I made it more complicated. Because I hope to use this formula to make it simpler in the next step. So it is the same as the limit y tends to 9 of y minus 9 square root of y plus 3. And in denominator, I have square root of y squared minus 3 squared. So y minus 9. So now, in the denominator, I do have a simple expression, y minus 9. And what's good about it, I have the same expression in the numerator as well. I can cancel out. As usual, y is close to 9, but not exactly 9. So I can cancel out. So it is the same as limit as y tends to 9 of square root, just square root of y plus 3, which is 6. The trick here, once again, is we want to simplify this expression a little bit, and most of all, we want to simplify this denominator. It's the most complicated here. And we make a kind of unintuitive step. In order to simplify it, we first make it more complicated by multiplying both numerator and denominator by this conjugate expression. But the reason we are doing this, at the next step, we will simplify the denominator using this formula. So, maybe questions about such a solution. We can do it also in a different way. Let me start the second solution. Maybe somebody sees how to do it. But yes, so use the same formula, but let's leave the denominator as it is. Let's use this formula in numerator. Let's factor this numerator. It looks kind of crazy idea. How do you factor y minus 9? Well, but let me write it as square root of y squared minus 3 squared. It is still y minus 9, but now it's obvious how to factor. I'll use this formula. So this limit is the same as limit y equals 9 square root of y minus 3 square root of y plus 3 divided by the square root of y minus 3. And now, once again, I can factor, I can cancel this part. And as we would expect, at this step we get exactly the same answer. When y is equal to 9, square root of y is equal to 3, and 3 plus 3 is equal to square root of y plus 3 is equal to 6. So in a way, both solutions had some slightly unnatural step. Here it was multiplying and dividing by conjugate expression. Well, it might be not natural when you see it for the first time, but well, as you keep solving problems where square root of something minus a number or square root of something minus another square root appear, well, when you keep applying this trick and it keeps working, well, then it becomes natural. And similarly here, the unnatural step was writing this simple expression in this form. It's really not natural, but well, it works. It helps you to factor it as a product of this thing and something else. So, do you have any questions about either way?
So if we get asked if someone could just use derivatives, that allowed?
So the question was whether you're allowed to use derivatives in probably L'Hopital's rule, something like this. So the answer is well. So first of all, we didn't cover L'Hopital's rule yet, and we won't cover it for maybe another 3 or 4. So I don't know how many weeks. If you do use it, well, make sure that you use it correctly. Because if you make even smallest mistake, we won't count it as if you well approach the question in the right way, but did a small mistake. We'll say, well, you just didn't solve the question. But if you do it correctly from the beginning to the end, then you get the points. There was another question. Yeah.
Wouldn't it be faster to substitute y?
Okay, we'll do it.
It's like the same thing as the other question.
Yes. So another remark is, well, in this question, this question is not really different from that question. It is the same question, but here y is kind of x squared, or otherwise f is square root of y. So maybe in this particular example, it's well, I mean, it is a reasonable idea. We'll try to do it in a different example, which is slightly more complicated than this one. But it will be helpful for us. Okay, so let me now erase this and move to the next example. Want to evaluate the limit of x over 1 minus the root of 1 minus s as x approaches 0. So let me do the first obvious step myself. When x approaches 0, the numerator approaches 0. The denominator approaches 1 minus square root of 1. So also approaches 0. So we can't apply the most naive argument. So what's the next step? How can we maybe simplify this expression? So we would like somehow to factor something out maybe, or manipulate it algebraically in a way it makes it simpler. So what's the idea? What can we try? Yes, the same idea as we did here. We have an expression with a square root. It might be helpful to multiply and divide both numerator and denominator by the conjugate expression. So first solution is about this algebraic trick. Let's take this expression, 1 minus square root of 1 minus x, and now multiply both numerator and denominator by the conjugate expression. Okay, now it looks, well, as we expected. The first step, it will look more complicated. What we want to do is open the brackets in denominator, not in the numerator. The numerator is good as it is. Denominator can be simplified. So we get 1 squared minus square root of 1 minus x squared, which is 1 minus x. And we leave the numerator as it was. Let's simplify it even further. This limit x tends to 0, x times 1 plus square root of 1 minus x. In the denominator, we have a very simple expression, just x. So after doing this thing, the denominator got simplified to just x, very simple thing. And what's even better, we have an x in the numerator, so we can cancel out. And now this limit is very easy to compute. When x is small, square root of 1 plus x is close to 1, and the whole expression is close to 2. So basically, the same trick. The only thing, well, the square root was slightly more complicated. Maybe algebraic manipulation was slightly more complicated. But otherwise, exactly the same thing. Sorry. Okay, any questions about this? Let's see another solution. see another solution. I have a complicated expression with a square root. And the most kind of annoying thing about this expression is the square root. So let me isolate. Let me introduce a new notation. I will call expression square root of 1 minus x y. Well, that's a good thing to find what is annoying and give it a name, but how useful is it? Well, my idea is then to rewrite everything here in terms of y. So, in particular, I'd like to know that x can be also expressed in terms of y. So then y squared is 1 minus x, and x is 1 minus y squared. So when I introduce this notation, y is square root of 1 minus x, I don't lose information. I can go between x, from x to y, and I can also go back from y to x. Now I will want to find some limit of some expression as x tends to 0. What happens to y? As x tends to 0, y being square root of 1 minus x, what happens to it? Tends to 1, right. And vice versa. As y tends to 1, x being 1 minus y squared tends to 0. So it's the same thing to talk about x becoming close to 0 and y becoming close to 1. And finally the expression x. Okay, so then the limit as x tends to 0 of x divided by 1 minus square root of 1 minus x can be rewritten using y. It's a limit as y tends to 1 now. Notice that y tends to 1. It's a new variable, it has a new limit. X. Well, I want to rewrite it in terms of y. Here it is. It is 1 minus y squared. Denominator. 1 minus, and this complicated expression is already y. We just called it y in the very first step. So now this limit which had a square root becomes a simpler limit which has no square root. So this trick of introducing a notation for the square root kind of eliminated the square root. And now we know how to solve such a question. So how do we solve it? Right. I see that the numerator vanishes when y is equal to 1, denominator vanishes. Let me isolate this y minus 1. So this limit will continue here. This limit of 1 minus y is 1 plus y divided by 1 minus y, which is the same as the limit as y tends to 1 of 1 plus y, which is, as we would expect, the same as 2. Yeah.
I have a question. For solution 1, you have the limit as x approaches 0 at x bracket 1 plus square root of 1 minus x. But then in the answer you have 1 plus square root of 1 plus x. I was just wondering how that changed.
So the question is about this line?
Yeah. Because previously you had square root of 1 minus x, and you have 1 plus x.
And incidentally just made a mistake. So this plus, well, it had nowhere to adhere from. It should be minus.
Okay.
choose. Other questions? So, whatever solution you prefer, you can use it. Just make sure that you use it correctly. So, understand at least one of the two solutions and understand it well. I mean, practice it on every example that you see. And well, each one of them has certain kind of pluses and minuses. Each one of them has slightly unnatural step. So here it is multiplication by conjugate expression. Here it is introducing the new variable and juggling between the two variables. So each one is good. I mean, I personally don't really have a preference. Yeah.
How do we know to use y equals square root of 1 minus x?
How would we know it? Well, basically I tried, well, my idea was to convert this expression to something without square roots. So let me take the square root and give it a name. So I've taken the most annoying part of my expression, I gave it a new name, then I hope that this will eliminate the appearance of this annoying expression. Other questions? Yes. So what both solutions you need? Okay, let's move on to see the more complicated example, but not really. Limit as x tends to 1 of square root of x minus 1 divided by x minus 1, and all this raised to the power x minus 1 divided by square root of x minus 1. So I have a complicated expression. Let me read it. It's the expression square root of x minus 1 divided by x minus 1, and all this raised to the power x minus 1 divided by square root of x minus 1. So it looks like a really complicated expression. But in fact, well, sometimes it might be misleading. The expression might be complicated, but the problem very simple. So for instance, if it were instead such a question, limit as x tends to 1, square root of x plus 1 divided by x plus 1, raised to power x plus 1 divided by square root of x plus 1. So if instead it was this question, it would be really, really, really easy. Because, well, how do we approach it? We just... Yes, so basically you just say when x is close to 1, this thing is close to 2, the denominator here is close to 2, the quotient here is close to 1, so we are raising a number which is close to 1 to some power. Moreover, this power is, well, x plus 1 is close to 2, square root of x plus 1 is close to 2, the quotient is close to 1, so we are taking a number which is close to 1 and raising it to power which is close to 1. So this is basically 1. So it's not true that a complicated expression always translates to a complicated problem. But here, unfortunately, well, yes, it does translate to a little bit more complicated problem than usual. So if we just try the same argument, well, when x approaches 1, this thing approaches 0, this thing approaches 0, the quotient, ouch, I don't know what happens. So the idea here would be, well, maybe it still approaches something. Maybe we just don't see it right away. So let's try to figure out. Maybe just this part of the expression does approach something. And then maybe this thing also approaches something. And then maybe we would be able to imply such kind of symbolism. So let's do it. First step, let's figure out the limit as x tends to 1 of square root of x minus 1 divided by x minus 1. So what would we use? Factor. For example, let's factor it out. T is the same as limit as x tends to 1. I can rewrite the denominator as square root of x minus 1 times square root of x plus 1. And, well, it's the same as limit as x tends to 1 divided by square root of x plus 1. When x is close to being 1, square root of x is close to 1. So this whole expression is close to 1/2.
Are you saying this one?
Sorry? So the question is what I was doing over here.
Yeah, so that's just separate.
Yes. So what I did is indeed I forgot about quite a big part of the question. I forgot about this exponent. I just am interested what happens when x is close to 1, what happens to this number. So this is not yet an answer to the question. It's an answer to a different question. Let me repeat the question. When x is close to 1, what can we say about this number? And the answer is, well, it is close to 1/2. So now we have some information, some new information about the original question. We want to raise a number which is close to 1/2 to some power. Well, let's figure out to what power. So in step 2, we'll figure out what happens to this exponent. Yes.
The first part, like the denominator is minus 1, and it turned into square root of x minus 1. So I don't really get that.
Oh, so here, so in this step I used the trick of writing x minus 1 square root of x squared minus 1 squared. Okay? And then I write it as a product using this formula a minus b times a plus b is a squared minus b squared.
Or is it conjugate after?
No, I just take this and I write it as square root of x minus 1 times square root of x plus 1.
Oh, okay.
Okay? So here I just factor the denominator using this trick. It's such a trick as such a product. Okay, so in step 2 I'll try to figure out what happens to the exponent. Is it true that as x tends to 1, the exponent becomes close to some number? So what would we do for this one? Okay, we can factor it, but we already know how to do it. I mean, let's do it differently. Let's, for example, multiply it, divide by conjugate. Just to have different ways. So multiply and divide both numerator and denominator by conjugate expression, square root of x plus 1. Then I'll open the brackets in the denominator. Once again, I leave the numerator as it is. Open the brackets in denominator. And it is x minus 1. And finally, I cancel out this x minus 1 and this x minus 1. And the answer is when x is close to 1, this expression square root of x plus 1 is close to 2. So I just solved this part of the question. Well, I decided to solve it in a different way, slightly different way. I actually could have noticed that it's actually the same expression, but just 1 over the previous one. And I could get the answer quite directly, but it's a good thing that we see different ways. Okay, and now we can answer the original question. Now we know that when x is close to 1, this thing is close to 1/2. This thing is close to 2. So in this whole process of computing this function, we raise a number which is close to 1/2 to a power which is close to 2. What is the result? Well, it's approximately 1/2 times 1/2, which is 1 over 4. So step 3 is actually finding the answer. Limit x tends to 1, square root of x is 1, so x minus 1, raised to power x minus 1 of the square root of x minus 1 is 1/2 squared, which is 1/4. So the idea in this question was, well, we want to calculate the limit of a complicated expression. And, well, we see that somehow parts of this expression don't make sense immediately. We don't see what they are close to when x is close to 1. Well, immediately at least we don't see what happens to it. So we take it, well, we compute this expression slowly, part at a time. So we take this part, which we didn't see what it is close to, and we compute what it is close to. Turns out close to 1/2. Then we take another part, and we compute its limit. Turns out to be 2. And then we argue as follows. This part of the expression is close to 1/2. That part of the expression is close to 2. So if I raise this to that power, I'll get something which is close to 1/2 raised to power 2. So the whole expression, the limit for the whole expression is 1 over 4. Questions about this example? So in general, you should be able to, well, given a complicated expression, try to split it to manageable parts, compute the limits of each part, and then, well, if it makes sense, make a conclusion about the whole expression. Okay, let's stop dealing with such crazy expressions. Let's try seemingly simple one. So here I have a limit quotient, absolute value of x divided by s. Just to remind you, absolute value of a number is basically this number, but without any sign. absolute value of 5 is still 5, but absolute value of minus 5 is 5. So you just disregard the sign. If there is a minus sign, you just throw it out. So, any ideas what this limit might be? So here the answer is 1, infinity, 95. So I guess that's the most popular versions. Let's try to figure it out. Well, I see that just when x is close to 0, both numerator and denominator are small numbers, the quotient apparently, well, hard to say what it is. I also don't really see how to factor things out because of this absolute value. So let me do it by just following the definition. Let's construct a table. When x is small, let's plug in some small numbers. Let's compute what is absolute value of x over s. And let's start, let's say, when x is equal to 1. Absolute value of x over x is 1 over 1, which is 1. Okay, but maybe this is not small enough. Let's take 0.1, 1/10. Well, absolute value of 1/10 is still 1/10, so it is 0.1. The quotient is 0.1 divided by 0.1, still 1. Okay, so to suspect something, when this is 0.0001, something like this, the quotient is still 0.001 divided by the same thing. Basically, applying absolute value doesn't change anything. And you get 1. So it's tempting to conclude that the limit is 1. Yeah?
What if we approach 0 from the negative side?
Okay, so in previous examples, when we did such a table, we always were careful to say, well, let's approach our limit from here, and also let's try to approach it from the other side. Let's see what happens from the other side. When x is, say, -1, this quotient, absolute value of -1 divided by 1, by -1, absolute value of -1 is 1. Just forget about the sign, so it is 1 divided by -1, which is 1. Sorry. So when x is -1, the quotient is -1. Let's try -1/10, -0.1. Well, quite similarly. The absolute value is 0.1, x itself is -0.1, and the quotient is -1. Similarly to -0.001, so it is -1. And our limit, well, what is the definition of limit? We say that the limit is equal to some number if as x approaches 0, so here as we make f smaller and smaller, the values of the function get closer and closer to some number. Unfortunately, here they do not get close to a number. These values are 1, these values are -1, and, well, the limit is what? Is it 1? Is it -1? Is it 0? Is it any number in between? Well, we just say that it's not defined. So this limit is not defined. In other words, it does not exist. So the intuitive reason why this limit should not exist is, well, when x is close to 0, which means when x is small, we just don't know what is absolute value of x divided by x. Kind of with equal probability, it is 1 or minus 1, depending on whether x is positive or negative. So the limit in this case just wouldn't tell you anything. It would say, I don't know what is the absolute value of x divided by x when x is small. On the other hand, we do see that there is some information which is kind of not reflected in this phrase that limit does not exist. We see that if x is positive, my expression is 1. When x is negative, my expression is negative 1. So I would like to have a phrase which tells me this information. So the phrase is like this. We say that limit absolute value of x over x as x tends to 0 from the positive side, from the right. This one is 1, and limit as x tends to 0, but from the negative side is minus 1. So let me write a definition. What do we mean when we write such things? So, say definition, limit as x tends to a plus f of x is some number if f of x approaches L as x approaches a remaining larger than a. And we also say that the limit as x tends to a from the left is some number if f of x approaches L as x approaches a remaining smaller than a. So here I just introduce a new phrase to our lexicon. We'll say that the limit of a function from one side, from the right. So this limit is called limit from the right, meaning that, well, you approach a kind of from the right, you stay bigger than a. So we say that such a limit exists if as x approaches a but stays larger than a, my function approaches L. So for example here, it would mean that as x approaches 0 but stays positive, which means bigger than 0, my function, well, is close to 1. In fact, in this particular example, it's exactly 1. And here, well, the other limit from the left, it would mean that as x approaches 0, so when x is small, but smaller than 0, so it's small but negative, my function is close to minus 1. So that's the concept of limit from one side. So looking at this table, this part of table tells me something about one of these limits, this one, when x approaches 0 from the positive numbers, and this part of the table tells me something about the other one, about this one, when x approaches 0 from the negatives. And together, they give me information about the limit itself. So here we can say that the limit of this function did not exist just because this information didn't match each other. This part of information didn't match this part. The limit from the right didn't match the limit from the left. So that's quite general thing. The limit of a function, just a limit, usual limit, exists if and only if, or whenever limit from the left agrees with the limit from the right. And both are equal to some number. So in the situation where both sides of the table converge to some particular value, L, I would say that just, well, my limit from the left, limit from the right, and the limit itself, all three are equal to L. On the other hand, it is possible, like we see in this situation, that one side of the table converges to something, the other one converges to something else, and there is no limit. There is a limit from the left, a limit from the right, and no limit at all. No limit in the usual sense. Okay, so I should ask how many of you did not understand what is the concept of limit from the right, one side. Okay, so we'll apply this concept now to some function which is not given by such a nice formula, like absolute value of something, or it's not really given by a nice formula. It is a function of the following type. So, example, maybe let me make a type function defined by cases. So the example is as follows. So the example is about cost of sending a parcel. So we know that in some post office, sending a parcel costs $10 if weight of the parcel is smaller than 1 pound. It costs $20 plus X if weight X is between 1 and 10, and it costs $0.3 a square if weight X is bigger than 10. So we have an imaginary post office with the following price list. If you want to send a parcel whose weight is at most 1 pound, you pay a flat fee of $10. If you want to send a parcel weighing between 1 and 10 pounds, you pay, well, $20 plus another dollar for each pound. And finally, if you want to send a heavy parcel, more than 10 pounds, you'll pay, well, quite a lot, 0.3 times x squared. So it's a function that grows very fast. And the first question is, here we have an actual function defined for us. For every weight of the parcel, we get a price. How to write this function mathematically? Well, we don't try to invent a new formula for in each case. We just say that my price function in this case is defined, well, case by case. We write it in this way. You put a curly bracket and we say that if my x is at most 1, then my price is 10. And maybe I should also make a restriction that it is positive, because it doesn't make sense to send a parcel weighing minus 5 pounds. Well, maybe if you try to send helium balloon, but anyway, let me make it like this. So then when x is between 1 and 10, my function is defined by the formula 20 plus x. And finally, when x is greater than 10, my function is defined by 0.3 times x squared. So I don't have just one formula, I have 3 of them. And each one of them applies for its own range of possible, well, x. So next question is, so this is just notation, how to express a function which expresses this weight, this price. Next question is like this. Suppose I want to send a parcel and somehow somebody told me that it weighs less than 1 pound. Somebody just assured me it weighs less than 1 pound. And I made a measurement at home and I found out on my own weight that it is about 1 pound. Well, my weight is not really exact, so I'll go to the post office and I'll have to pay something. So the question is, what will I pay? And for me, it is a question about the limit of my function when x approaches 1 from the left. So what do I mean? I mean, it's how much will I pay if my weight is approximately 1 pound, but guaranteed to be smaller than 1 pound. So that's the meaning of this expression in this particular problem. And how would we find this thing? I mean, it looks complicated because my function is complicated. It's defined by 3 different expressions. Which one would I even use? First one. Right. So here I know that x, well, it is close to 1. But I also know that by the definition of this limit from the left, it must remain smaller than 1. So here, in this case, I want to evaluate my function for value of x, which is smaller than 1. Yes, it is close to 1, but still smaller. So it is the same as limit as x tends to 1 from the left side of just this expression, 10. And what is this limit? 10, of course. This function is just for every value of x, it is 10. Okay, next part. What if I know that my parcel weighs more than 1 pound, but still close to 1 pound? How much would I pay? So the question is, I want to evaluate this function when f, I want to find the limit as x tends to 1 from the right. Well, in this case, which one of these formulas would I use? The second one, right. So now I know that x is close to 1, but slightly larger. So I'm in this case, when x is larger than 1. But still not here, not in the third one. I still know that it is close to 1, so definitely not greater than 10. So I'm here. So it's the limit as x tends to 1 on the right side, 20 plus x, which is 21. So when x is close to 1, this is close to 21. What about the actual limit? So now the realistic situation. I make a measurement at home. I know that my weight is about 1 pound, and I want to ask how much would I pay. So what is such a limit? Limit as x tends to 1 of my function. Right, it just doesn't exist. So this does not exist. And the mathematical reason is this statement. The limit from the left does not agree with the limit from the right. And intuitively, in this particular problem, it's just, well, if you tell me that your parcel is about 1 pound, weighs about 1 pound, well, I'll have to confess I don't know how much you will pay. It will either be close to $10 or to 21. I have no idea what it will be. And here, this limit does not exist. Okay, let's try to understand what happens when this other final point, when the weight is close to 10. So limit of my function of x tends to 10 from the left. What is it? Which formula do I use? The second one. My x is close to 10, but still smaller than 10. So I'll use this formula. X, and the answer is 30. The limit as x tends to 10 from the positive side, from the right. What formula would I use here? Right, the third one. Because now my x is, once again, close to 10, but now larger than 10. So I'm using the third formula. Limit as x tends to 10 plus 0.3 x squared. And its limit is 0.3 times 10 squared, which is 30. Cool. And finally, limit as x tends to 10 of the function itself. So when x just tends to 10. 30. Right. Now my limit from the left does agree with the limit from the right. Even though they come from different expressions, somehow they do agree. So the limit itself is 30. So in this situation, if somebody tells me, well, I know that my parcel weighs about 10 pounds, how much do I pay? Well, now I will confidently say about $30. Let me draw a graph of this function so that you see visually what happens. What is wrong with this point and what is right with this point. The function looks like this. F x. So for x, there are two important points. One is x equal to 1, another one x equal to 10. When x is between 0 and 1, my function is defined to be 10. So here I have such a horizontal line. When x is between 1 and 10, my function is defined to be 20 plus x. So it starts being 21. Oh, yes, so in most cases, sorry. I'll draw it here. So when x is between 0 and 1, my function is 10. When x is between 1 and 10, my function is 20 plus x. So it starts at 21 here and grows all the way to 30. And finally, when I go from 10 to the right, I have a quadratic function, quadratic polynomial, but you see that its value at the point 10 is exactly 30. So it is a part of parabola. So it should imagine that there is a parabola here, like this. But somehow at this point, well, the two values do match. So you see that at this point, at point 1, there is a jump in definition of this function, in just how it looks like. That's why the limit does not exist. You approach one from different sides, you get different limits. And, well, to make this graph precise, you have to also take care of what happens at the point 1. So at the point 1, we use not this definition, but rather this one. So to make sure that we don't confuse the two definitions, we put an empty circle like this. So the agreement is whenever you see an empty circle, it means that the obvious continuation here doesn't work. So this means that at the point 1, well, it's not this line, but rather this line, which defines the value. So the value of the function at this point is 21, and that's how the graph looks like. Okay, so I didn't have time to talk about this theorem, and there is one question in the homework assignment which uses this theorem. So I guess I'll put on the website something about this, and well, you should look in the book and see what this theorem is. But I will discuss it next time.